All right, let's just dive right in. When you hear the word matrix, you probably think of these dense math textbooks or maybe classic sci-fi. But what if I told you it's actually one of the most profound ideas we have for understanding reality itself? In this explainer, we're going to unpack the matrix, not as some scary equation, but as a language, a grammar for how the world really works. I mean, just think about it for a second. Everything is a system, right? The weather, the economy, even a simple conversation. But how in the world do you capture the rules that govern it? How do you write down that invisible logic that connects all the moving parts? That's the huge problem we're talking about today.
And here's the core idea from our source material that just clicks. Nothing means anything by itself. An object, an idea, a person, their real significance comes from how they relate to everything else around them. And this is where the matrix comes in. It's the tool we use to describe, to measure, and to actually play with those connections. So, here's the crucial takeaway. A matrix isn't just a box of numbers. No way. You've got to think of it as a formal language, a kind of grammar for what the source calls relational intelligence. It's how we take this messy, tangled web of a system and translate it into a structure we can actually get our heads around and even change. Okay, so if the matrix is a language, then what are its building blocks? Let's break down the essential nouns and verbs of this grammar for reality. This is where the whole idea just becomes so incredibly elegant. Abstract concepts map right onto algebra. So the things in your system, people, particles, stock prices, whatever, they become vectors. Just think of them as a snapshot of their state. The rules, the interactions between them, those become matrices. And how does the system actually change over time? Well, that's just matrix multiplication. It's how the system evolves. Simple as that. Let's take a closer look at vectors. And hey, for a moment, forget that image of a simple arrow you learned in school. A vector is really a complete description of something at one single point in time. It captures all its properties, all its degrees of freedom. It's the what that the matrix, the operator, is going to act upon. And this right here, this shows the beautiful symmetry inside a matrix. The rows and columns, they aren't just there for looks. They're duals of each other. A row can represent the constraints on a system, the action it performs. A column, on the other hand, represents a dimension of its state, its configuration. It's literally two sides of the same informational coin. Pretty cool, right? All right, now that we've got the basic language down, let's take a quick tour through a gallery of different types of matrices. Think of each one as a unique kind of operator, a specific verb in our grammar that does something really powerful and distinct. First up, we've got the simplest one of all, the identity matrix. Think of this as the baseline, the sound of silence. When you apply this matrix to a system, absolutely nothing changes. It's the operator of perfect stasis. It's the ultimate preservation of what is. And then, in total contrast, we have its exact opposite, the zero matrix. This thing is the operator of annihilation. It takes any state, any vector, and just crushes it down to nothing. It represents a total collapse, the complete erasure of all information. So you go from perfect preservation to total annihilation, the two extremes of transformation. But of course, the most interesting stuff always happens somewhere in the middle, doesn't it? Things aren't just staying the same, and they're not just disappearing. They're changing in an orderly way. So what about transformations that move things around, that create change, but still preserve the essential structure of the system? Well, that brings us to the orthogonal matrix. A great way to think about it is like picking up a rigid object, say glass, and just turning it in your hand. The glass is now in a new position, but its shape is perfectly preserved, right? That's an orthogonal transformation. It's pure rotation or reflection, with zero distortion. The relationships between all the parts stay exactly the same. It's change without corruption. Now for a really fascinating one, the nilpotent matrix. This is an operator that, well, it just fades away. Imagine a ripple in a pond. If you apply this transformation over and over and over, its effect gets weaker and weaker until it eventually just becomes the zero matrix. It vanishes completely. This is a brilliant way to model things that are temporary, things that fade out over time. So we've seen these different types of matrices, but how do we actually use them to solve problems? Well, that's where a process like Gaussian elimination comes in. Think of it as a super methodical way to clean up and simplify a really complex system. You represent the system as a matrix, you follow a set of simple rules, and boom, you strip away all the complexity and all the noise to find the clear, fundamental answer that was hidden inside.
The source calls this epistemic purification, which is a powerful way of saying we're purifying our knowledge of the system to get right down to its core truth.
And when you purify a system like that, you can find its deepest truths, its eigenvalues. Okay, imagine you're stretching a rubber sheet. Most of the points on that sheet are going to move and change direction, but there are these special directions that only get stretched. They don't get rotated at all. Those directions are the eigenvectors, and the amount they get stretched by, those are the eigenvalues. They represent the stable, core properties of the transformation. It's why the source so poetically calls them the resonant frequencies of the system. They reveal its essential, unchanging nature. Okay, we've looked at the building blocks, we've seen the operators. Now let's zoom all the way back out and connect these ideas to the biggest picture possible and see how this isn't just math, but a fundamental code for reality itself. And this slide right here, this is the real payoff. Just look at how this one idea, the matrix, is the foundational language across so many different fields. In physics, it's describing the quantum world. In computing, it's the absolute bedrock of AI. In systems theory, it teaches us that structure comes from relationships. And in cognition, it defines intelligence itself as the ability to understand connections. It's a universal metamap.
And this brings us to the final, powerful conclusion from the source. Meaning isn't some static thing that you just find. It's something that emerges. It materializes when one thing acts on another, when a system evolves, when a state is transformed. Understanding isn't about knowing things in isolation. It's about understanding the rules of how they interact. So I'll leave you with this last thought to chew on. If this grammar truly is a code for reality, and if every system is governed by a principal transformation matrix, what the source calls its key matrix, then what is the key matrix for reality itself? What's the fundamental operator that governs the evolution of everything? Now that's a question worth thinking about.